Thanks, Leslie. This is John Budreski, and Ian will go through a good portion of the slides today on the some of the case studies and the interesting stuff. So as usual, I get to go through some of the more dry background information on what we're doing and any regulatory updates and UAS updates. But AirShark is a service provider of data collection using UAVs all over the country. We get started here in Vermont in 2014, and we inspect infrastructure and do quite a bit of mapping associated with that. In today's webinar, we'll be focusing on UAS, or Unmanned Aerial Vehicle LiDAR. Get into the technology a little bit, and we'll have plenty of time for discussion. We'll talk briefly about just the regulatory updates, because that's always sort of a constraint and been somewhat of an inhibitor, but that's finally changing this year and last year. Look at the specs of the particular sensor we're using relative to data collection, go through some example projects, like I said, and kind of look about what's around the corner. We don't always know, but there's questions we get from customers that we can talk about as well. So hopefully we'll wrap up well before lunch with a good discussion today. So all of this obviously has been enabled by the smartphone technology with incredible data processing capability, the sensors, et cetera, et cetera. Now we're essentially putting these devices in the sky to augment and assist in various forms of data collection. And a lot of our projects revolve around infrastructure, like I said, or environmental projects. And the amount of processing that goes on is still pretty mind-boggling. So sometimes it takes a day or two to churn through the data, but all of this was sort of enabled by a lot of the smartphone technology, less so than the military technology. So we'll talk about some of this. Next slide here. In this world today, we're in the small UAS space, or sub 55-pound category, and it's under the FAA rules. It's the Part 107 world. This means that there's limited flight times. We're not going for hours at a time or hundreds of miles. We're still sort of operating in a box. We can make that box larger by essentially asking for waivers. And we're operating in this regulated airspace. So here in Vermont, for instance, we have a great area to operate because a lot of the airspace is still Class G, meaning we can operate outside of busy airports, for instance, or congested areas. And most of these LiDAR flights today that we're doing are on multi-rotor platforms, because the sensor is still, even though the form factor has come down greatly, the sensor is still about 7 or 8 pounds. So the multi-rotor platforms hold the actual LiDAR sensor. And just a quick summary, haven't changed a lot since our last webinar. We're still generally operating in line of sight, meaning wherever we can see the drone or the UAV. Oftentimes it's several thousand feet either side of us, and that's up to a mile sometimes if you go left to right, if you're in an open area. Sometimes because of tall trees, we have to tear down and set up a site and move the base station in the case of the LiDAR rig. So that is really the most significant rule we operate around, and also the airspace. Like I said, typically outside of busy airports and 400 feet or less, although we can get waivers to operate on airfields and higher. Some of you have seen this slide, just like to hook it up again. Important to just plan projects and be cognizant of what we need to do as an operator if we're collecting data for customers, whether it's state or federal or an engineering firm, for instance, or we're assisting on a partnership project. Obviously working backwards from data types, what is needed in the end, and then figuring out what aircraft, what insurance, what types of software we're going to use to process some of this LiDAR data. And Ian will talk about some of that today.
Yeah, and that's kind of where I'll jump in and kind of go from here. My name's Ian Ray for those of you that haven't met me, I'm the Chief Technology Officer at AirShark and Media Wing, and I'm primarily focused on our GIS capabilities and the delivering of data to clients and capturing data in the first place. So one of the big things that's recently become available in the last year or so is LiDAR platforms that will actually fit on aircraft in the sub 55-pound world, which is the FAA requirement for small unmanned systems. There are a couple of sensors out there. The sensor that we've been operating recently operates in the 100 to 250 meter range. And in those ranges, the accuracy of the data that comes back is in the 2 to 5 centimeter world, up to 10 centimeters if we have to fly a little bit higher to cover a little bit more area. Most of the LiDAR sensors out there that sit on these types of platforms do also have onboard RGB cameras. Some have multispectral or thermal cameras as well that allow you to colorize the points and be able to work with the data that way. And the big takeaway for us and for drone-based LiDAR in general is that the point density that comes back is substantially higher than most publicly available data sets or even a contracted manned aerial LiDAR flight. We're working in much smaller areas, usually in the 50 to 100 to a few hundred acres per project world. But in those areas, we can get 30 to 100 plus points per square meter and do that with a multiple of returns for post-processing. Just to give you an idea, again, of kind of what these systems look like. On the left is the aircraft platform that we fly. It is a DJI-based system. It's got 6 rotors, and including the payload, batteries, the whole 9 yards, and all the GPS equipment involved, it weighs about 35 to 40, and it weighs about 38 pounds, give or take. The system a little bit closer up on the right gives you an idea of what the LiDAR sensor itself, plus all the processing equipment that's on board, the small Linux computer that drives it. That's kind of what it looks like up close. So one of the things that we want to do is just kind of walk you through a couple of projects that we've done recently with the LiDAR system to kind of bring up discussion and kind of get you thinking about how LiDAR might work for your projects. I'll also wrap it back around because many of you have probably looked at using drone-based photogrammetry for some of your projects. And that is another great tool that can either augment or, in some cases, be compared against a LiDAR capture. And I'll talk a little bit about why you might choose one over the other and where the LiDAR really comes out ahead. So one of the biggest places that a LiDAR capture versus photogrammetry really has its advantages is anywhere that involves vegetation or trying to pull terrain out from under vegetation. This is an example of a wastewater treatment plant that also had a solar array placed on it. And one of the questions that we were asked is, can we go in and start working on doing analyses that will help for solar shading, see if there are any issues around some of the vegetation encroaching on the solar arrays. And so just to give you an idea of what some of the data looks like after we've gone out and done a scan, this is kind of what we're looking at. One of the nice things we can do is very quickly do analyses that will tell us the individual tree locations and also how tall those trees are. So in this case, we were quite interested to see the vegetation that was right next to the array and see if it was actually going to be shading anything. In this case, we were using this project as a case study and knew that this particular tree was not going to be shading the area. But we were very quickly able to go in and determine how tall it was and the approximate area that it was covering. Another kind of image that just gives you an idea of what the project area looks like. We've got the solar arrays actually just under the profile view that I've drawn. You can see all the individual trees that have been automatically extracted. And this is just a profile view that gives an idea of what the vegetation and the ground after they've been classified look like. Now, ignore the orange areas that say that they're buildings and didn't quite clean up some of those areas quite just yet. Again, just another quick detail of what that project area looked like in a profile view of the solar arrays themselves. So from from a less dense point cloud, you might only get a few returns off of the solar arrays, or especially off of very fine details like this. But the nice thing about capturing in that 30 to 50 to 100 points a square meter world is that there's a lot of density to extract a lot of details very quickly. Another project that we've worked on recently, and a place where the LiDAR data was very helpful, was on a beach erosion project that we worked on. One of the concerns was these quite expensive beachfront homes are slowly losing their backyards as time moves on. So the beach keeps coming in, we've got hurricanes, we've just got climate change and everything coming in and affecting the beachfront. And as you can see, some of the areas have been armored in an attempt to slow that process. So one of the reporting requirements is to go in and look at how that armoring is performing, and see if any work needs to be done to maintain them. So this is a colorized output from the LiDAR point cloud that we ran on the site, and this is an example of how it compares against traditional survey. So the problem that to go back a slide, the problem that the surveyors had when doing this with traditional methods is that they would go out and do topo of both the ledge and kind of the edge of the beachfront on top of the bluff, and then also go down and do topo out a few feet into the ocean and everywhere in between. The challenge is it just wasn't safe to actually climb up the bluff. And so the data that came back was always interpolated in the steep areas of the bluff itself. Now, this was an area that we went in and did both photogrammetry and LiDAR as a comparison for this client. And as you can see, both the photogrammetry and the LiDAR data came back with a much higher level of detail than was doable through the interpolated topo in those steep areas. Throughout the comparison, we were across the entire project area. We were about a plus or minus a tenth of a foot, and actually less in most areas, with both the LiDAR and the photogrammetry data. So, another project that we've done recently that was very well served in kind of a new creative use for using LiDAR is looking at railroad bridges. We've been doing a lot of work in the utility and rail sectors, looking at assets that have been in the field for possibly hundreds of years. So this was a railway alignment that has a bridge on it that actually the railroad doesn't even have plans for. So one of the challenges that happens is you have assets that are 100 years old and don't know much about them other than ongoing inspections that have been done on the asset. So we came out with the LiDAR sensor, and this is both a great example of where the vegetation capabilities of a LiDAR capture come into play, and also the individual structure captures become really important. So nice thing about doing a LiDAR scan in this area is that we got very high accuracy data of the railroad bridge and the entire right-of-way. So we can look at vegetation encroachment into the alignment, and we can also look at the individual bridge and the individual members of the bridge itself. One of the pieces that was of interest was to try and recreate a bridge plan of this bridge and be able to do that with fairly accurate dimensions to it. So we took the LiDAR data set, shaved off some of the vegetation, and started looking at the bridge and began the process of building an interim bridge model for loading analysis and for more generalized engineering work on the structure. One of the questions we always get when we do that is, how accurate does it get? And again, this is where we get back to the accuracy of the sensor. We get about the 2 to 5 centimeter accuracies with this type of data, which is fantastic for generalized modeling. One of the questions we do get, though, is can you measure how thick the steel is? And that's pushing it a little bit. We can't quite measure at that level of detail just because the sensors are not quite that accurate. In this case, though, an engineer with a set of calipers combined with the LiDAR data set has provided a lot of information to the client and been something that we've been able to really prove a lot of value from the aerial capture. So one of the things that always comes in as part of the workflow for working with any of the LiDAR data is what does it actually look like to process, and what do you need to get out of it? So as I've been talking about, the LiDAR system itself is an active sensor. It's firing laser pulses out into the world and measuring the returns that come back from them. One of the things we can do is either use onboard cameras to colorize that data and also generate ortho images, or for higher resolution data, generate ortho images from another aerial capture flight with a higher resolution camera. So depending on what the needs are, there are several pieces of data that move around through the process. In the LiDAR capture, it's generally an initial LiDAR point cloud, the flight trajectory, and then any images that are associated with it. So working through the processing software and or photogrammetry software such as Photoscan or Pix4D, we can come out with both the point clouds and ortho photos that can be loaded into your GIS tool of choice. From there, either our organization or the end user themselves can use that data to do all sorts of things. So this kind of gives a general idea of what goes into processing that data and the types of things that you can get out of it. One note that I always like to mention when clients are looking at LiDAR is comparing them against photogrammetry and determining whether a LiDAR scan is necessary or will provide more value than a photogrammetric scan of the same area. The advantage to a LiDAR scan is always that it will capture very fine details at a very high accuracy, whereas photogrammetry is much better suited for larger areas that are flat, continuous surfaces. This image is actually a perfect example of where the photogrammetry starts to break down. So as you can see in the photogrammetric point cloud in front of us, the vegetation becomes very difficult very quickly for any image-based capture system to reliably detect. But as you can see, the flat surfaces and the roadways really came in very well. And those, compared against the LiDAR data set, are almost identical results. If you're generating 1-foot contours or if you're generating surface models, a LiDAR data set and a photogrammetric data set in those open areas is going to be very similar. And again, the areas where, as you can see, it starts to break down is in those vegetated areas. So for this client, the interest was solely of the landfill itself, and so photogrammetry was the perfect use case here. However, if the question had been, we're looking to expand to the west, we need to know what's under that tree canopy, that's where I would suggest a LiDAR scan instead. And again, just one kind of parting set of images just from a photogrammetric capture is, again, the type of solar array in an open area that would be perfectly suited for LiDAR or for photogrammetry, which is a lower cost option as opposed to bringing out a full LiDAR sensor suite. And again, generating both surface models and contours to do that. So that's a very quick overview of some of the LiDAR projects we've worked on, and the hope has been to kind of talk through this pretty quickly, and in the hopes that it's generated a couple of questions from the audience. A lot of times when we show LiDAR data, at the end of the day, we're looking at points, and really the question for us is, how does that get applied to a specific project or a specific use case? So with that, I'll play this video and, oops, maybe I'll play this video. There we go. So I'll play this video in the background and kind of look back to Leslie to see if any questions have come in from the audience, or if there's any questions in general that kind of have been prompted.
Thanks, Ian. So this is Leslie, and I think people are pondering and typing in their questions as we speak. But one thing that I may have missed, or so I apologize if I'm asking something that you actually already answered. But can your UASs carry more than one sensor at a time?
Great question. So generally speaking, yes. The aircraft that we've configured specifically for LiDAR capture operates the LiDAR sensor itself, and it has a bore-sighted RGB, or visible spectrum camera on it as well. So that's one of the multi-sensor payloads we have available, specifically for the LiDAR capture. If we need to do multispectral capture, thermal capture, there are ways to do that either by integrating those sensors onto the platform that has the LiDAR sensor, or doing those as separate flights with a separate aircraft and then merging the data in post. So we can fly multiple sensors if need be, if we do need to be capturing data at the same time, or depending on the project need, we can be flexible and use multiple sensors across multiple aircraft.
Okay, so here are a couple of questions. What is a ballpark cost for a system like is being shown, UAS and LiDAR sensor? Are you using Global Mapper for processing your LiDAR data?
So both great questions. The aircraft, so the overall cost of the system that we're operating is in the $200K range all in when you get into the aircraft, plus the sensor, plus enough batteries to actually go out in the field and do it, and all the supporting equipment that goes into it. Now, having said that, we have bought a pretty high performance sensor. If you think about the sensors on a kind of a good, better, best spectrum, we've bought the better sensor. And we did that specifically because we needed to be able to detect power lines, bridges, and very fine details at very high density. Now, there are sensors that are available. For example, the sensor itself is in the 130 or 140 world of that total cost. There are sensors that start at about $50,000 to $60,000 and go up from there. And when I say sensors, I mean the sensor payload. So that's a sensor plus an inertial system plus a onboard computer to log all the data, plus a survey GPS. So there are systems out there that are lower performance, may not have the range or the density of the sensor that we're using. And there are sensors that are close to, that are into the $300,000, $400,000, and $500,000 range that have even more range performance and even more density that comes out of them. So it kind of depends on the project. If you're looking for, if you're looking to bring a LiDAR sensor in-house, that's the kind of the price range that's in the market right now. Again, for the sub 55-pound aircraft world, there are obviously systems that are larger and more capable that that would require larger aircraft. The other question that was posed was, do we use Global Mapper for processing our LiDAR data? Generally speaking, yes. The actual processing of raw data from the aircraft into a LAS or LAZ file is run through a vendor-specific piece of software plus an inertial trajectory management software that fuses our RTK GPS data, or I should say PPK GPS data, and gives us the accurate position of the aircraft. So we run through a suite of software tools to process the inertial data, then process the LiDAR files. And from there, we can take the point clouds into whatever package that we that's needed. You can take that into ARC, you can take that with a little bit of work directly into Civil 3D. In our case, we found that Global Mapper provides the ability to work with the data very quickly. And for the majority of the things that we're trying to do, generate surface models, generate contours, and do basic analysis on the data, that's been the quickest tool to do those things. Obviously, heavier lifting, ARC, Civil 3D are kind of where you get into a little bit more detail.
Okay. And kind of a follow-up to that or add-on to that is, can you give a cost estimate for photogrammetry hardware as a comparison?
It's a great question, and it's why I ask and I kind of talk about, do you need LiDAR as compared to photogrammetry? So in comparison, a photogrammetric system, a photogrammetry-based aerial system that will allow you to capture at high detail and get high-quality results repeatably, emphasis on repeatably, is in the about $20,000 to $30,000 world, all in. And I say that because it's not just the aircraft that you'll find that you can get for $2,000 or $5,000 or $10,000. It's that plus all of the ground supporting equipment, plus usually 6 to 15 plus sets of batteries for a field operation. We've had projects where we've flown, where we've burned through 12 or 15 sets of batteries in a day. And the batteries, get pretty expensive pretty quickly.
Mm-hmm.
So I generally say if you're looking to get into it, if you're looking to experiment with it, you can get into it for a few $1,000s with some of the lower cost systems that are out there. Again, focusing on batteries and transportability and all the equipment that goes with it. But to do it at a commercial level, to be hitting these, 2 to 5 centimeter accuracies, you do want to have the better cameras, you do want to have the better sensors, and you do want to have systems that are just built to go into and out of the box every day without breaking.
Yep.
So that's kind of the comparison of the photogrammetric versus the LiDAR capture. Now, for us as an organization, delivering that, as opposed to selling the hardware, delivering that as a service, generally speaking, the cost of a LiDAR scan is about double the cost of a photogrammetric outing. LiDAR scans by default require 2 staff members, where sometimes you can do a photogrammetric scan with 1 staffer. And then just the cost of the equipment and cost of the back office processing, the whole 9 yards. The service cost is roughly double for a LiDAR scan.
Okay. And in relation to the resolution and accuracy that you mentioned a second ago, is the 2 to 5 centimeter accuracy derived via onboard RTK or with GCP ground control? And also, is it reflective of both horizontal and vertical accuracy?
It's a great question. So for the LiDAR scan, the outputs are that accuracy without follow-up control. So the onboard system is capturing a RINEX data on the aircraft, and then we have a RINEX base or go through the CORS network to pull RINEX data and post-process that data, which gives the resulting point cloud that level of accuracy without any ground control. Now, of course, we almost always have control on site as a QA step and for for verification and sanity checks. But one of the nice places to do a LiDAR scan is in areas where you just can't get control. For example, we've scanned several salt marshes that are just an absolute bear to put a surveyor out and actually get shots, in the mud and in the muck. So we can get that level of detail or that level of accuracy with a LiDAR scan without necessarily having ground control on site to measure against. Comparatively, the photogrammetry requires ground control to be able to do that. There are systems that are out there that do RTK or PPK-based photogrammetry that, in theory, on a good day, can also hit those accuracy targets without control. However, they're finicky at the moment. And that's been what we've been our experience. There have been, there are people getting fantastic results out of them, but for the best results from a photogrammetric process, you always want to have a substantial amount of ground control. Usually between 5 to 10 shots per 50 acres is usually the rough back of the napkin number that I put out there. So that is part of the process for photogrammetric capture with high accuracy. If all you're interested in is a rough ortho photo of the scene, for example, for emergency response or just for, maybe less analytical data and more, subjective observations, that can be done without control, and that will just drop in at the accuracy of civilian GPS. But that is a big difference between the two systems, at least in our fleet right now. And it's something that we always kind of mention to clients when we go into discussing a project.
Okay. And then another question is the Pix4D software good for, do you find it to be a good software for photogrammetric compilation?
Absolutely. We're Agisoft Photoscan shop just because that's the tool that we've become comfortable with and have been using for a few years. Although I have spoken to and work with folks regularly who use Pix4D with equally successful results. So I would say either Pix4D or Photoscan are great choices. Anything outside of those two, I would take a pretty hard look at before hitting the buy button, just because those two are really the industry standards. Pix4D also is a little bit more user friendly. I will say that. Photoscan is a little bit more convoluted to work with, but also gives a couple more options that allow you to pull good data out of less than ideal captures, where Pix4D tends to choke on data if it's not kind of perfect. For example, if the exposures are off, or if the images are a little soft or blurry, Photoscan seems to be a little bit better to pull data out of those. But yeah, can't go wrong with either choice. They're both great pieces of software, and we've tested and used both, and they're great.
Here's a question about the software. What software do you use for the automated flight plans?
We use a couple of different pieces of software depending on what we're trying to do. For the LiDAR scans, we actually do a lot of our planning with an open source tool called Mission Planner, which is actually built for the ArduPilot systems. Excuse me. And that piece of software allows us to get a generalized idea of what overlap we need for a specified quote unquote camera width or camera footprint. In this case, it's a LiDAR footprint, but we have the same basic idea. We have a width that the sensor is going to capture good data in. And we use that piece of software just because it's quick and it's available. What we usually do is load that into a piece of software called Autopilot on the iPads for any of the DJI-based systems, which our LiDAR aircraft platform is. And that allows us to drive any of the flight grids that we've created in other software. Generally, if you create a flight plan and can get it into a KML, you can load it onto this piece of software called Autopilot on the iPad, and that will allow you to actually fly whatever grid or whatever line you've put into it. One of the challenges with that is it works really well for doing flat areas where you don't need the aircraft to change altitudes during the scan. Terrain following is very difficult. So if we're on the side of a mountain, for example, if we haven't done this with LiDAR, but if you're trying to automatically fly up and down a ski resort, to keep it Vermont specific, you'll have some challenges getting the aircraft to actually be able to follow that. It becomes a very big dance and a very cautious dance to make sure that you're changing the altitudes and make sure that you're keeping off the ground. One of the big things that not a lot of people know about UAVs is that for the most part, their altitude reference is relative to where they take off. It's not actually relative to world frame at all. So if you take off if you say I want to be 200 feet above my takeoff location, and then you fly up the hill 200 feet vertically, all of a sudden you've just flown into the side of the trail. So that's one of the places that there really aren't very good pieces of software, at least for the DJI-based platforms, to manage that. So what we end up doing is we actually use a much lower cost platform as a trial run before any of the more complicated LiDAR scans. We'll actually go and run the entire thing with a platform that costs a couple $1,000s, and just make sure that we're not running into anything, make sure that we're keeping good clearances from any power lines or structures or towers or whatever, and make sure that we're staying out of the way and not going to run into anything. So that's kind of been our approach to it. And frankly, if anybody has a better suggestion for iPad or iOS specific apps, we're always interested, and we're always trying to keep our eye out on them. So we're still learning as well on a lot of this stuff.
Do you have any open source software recommendations for photogrammetry? And this is from someone who's currently using OpenDroneMap.
I have looked at OpenDroneMap a little bit. I forget exactly what the project is called, but OpenSFM, I believe is it, or the Structure for Motion toolkit that's out there. I experimented with it a bit to see if we could, use it to get good data. I wasn't very thrilled with the results, but that was over 2 years ago at this point was the last time I really looked at it. I'm not aware of any projects that do it very well, at least for mapping purposes. There are some projects that seem to do pretty well with object-based things if you want to document a statue or something like that. But one of the suggestions I would make would be to look at, go back, look at Pix4D, look at Photoscan, also look at Global Mapper. They actually just released, it's not open source, but it's pretty low cost. Their newest update to the LiDAR module added capability to do some limited photogrammetry processing. Now, it still needs a lot of work to catch up to Photoscan or Pix4D in terms of capabilities, but it does seem to, it does work, and it is available in a tool that I would recommend people have in general. I think for the cost of a license, or even the cost of a license plus the LiDAR module, which I think it's 500 piece for the license and then another 500 for the module, you can't really go wrong with it as a piece of software. And I believe that's a perpetual license. So shameless plug for Global Mapper there, I guess, but it's worked really well, and that might be another option to look at.
I just wanted to add something else. So Leslie, on the planning side, I'm often on the front end with customers, and with UAS, sometimes it's problematic to achieve results unless you're creative, time of day, locations, aircraft, and going back to what do you need to get done? Do we need this aircraft? And Ian was recently involved in a project, and we can stay away from an area we really don't want to be over with the wide swath of the LiDAR scanner and still achieve results with photogrammetry and the narrower field of view. Sometimes that limits us to being kind of right on top of something. So there's some low and slow and creative ways that we can stay to the side of a location and still capture good data. And that also brings up the point of having a live feed. So we have a plug-in on the aircraft. So whether it's us or the customers that are out there collecting, or they're eventually going to use the data, they can actually see in situ as it's collecting the data, which is incredibly valuable sometimes. I mean, probably great for accident reconstruction or something, but also just to see, is it working? Are we collecting good data? So there's some level of QA in the field happening.
Mm-hmm. And there are a couple of recommendations from our audience. Megan suggests Tower app for flight planning. She said that's an okay software. And then Dave suggests Map Pilot. I'm not sure if that's flight planning or if it's, anyway, it has terrain awareness, but uses SRTM data for terrain, so not really a precise solution.
Yeah, and that's been one of the challenges we've seen. I think I looked at Map Pilot a while back, and one of the challenges was it's how good is the underlying terrain data. I definitely would suggest for any LiDAR captures or for anyone that's thinking about doing terrain following, even if you're doing it for photogrammetry, is definitely do that with a test run and have your finger on the button to cancel the mission if it looks like you're getting close to stuff. So.
Okay, that's all I have right now. If people have any other questions, this is your chance. And if you guys have anything else you feel like hasn't been covered, oh, I know, I did have a question, my own. Do you use fixed wing aircraft? And then if so, have you done any LiDAR collection with them yet?
We've used fixed wing on occasion, and we're actually looking at picking up a fixed wing aircraft for photogrammetry. Actually, one of the systems that does have RTK capability. We don't have it yet, but we've seen a lot of good results from some of the platforms that can do photogrammetry from fixed wings, and it allows you to cover a bigger area. Kind of like I was saying earlier, is the LiDAR scans are limited by their flight time. It's a big aircraft, a lot of very expensive batteries that only get us about 10 useful minutes in the air, about 12 to 14 minutes, including the takeoff and landing. And so in that time, we can scan, depending on the area, anywhere from about 20 to 50 acres in a single pass with those systems. The nice thing about using the fixed wing, especially for photogrammetry, is you can cover hundreds of acres in a flight and get good data from it. So we haven't looked at using fixed wing platforms for the LiDAR because it starts bumping up against the weight limits that the FAA has set for us. I am aware that the LiDAR vendor that we've worked with to get the sensor running, Phoenix, they actually have just started shipping a aircraft that with the sensor we have is, I believe, like 53 pounds or something like that. So it's just under the requirements to do that. So it's something that we're looking into, but at the moment, the other part about doing fixed wing flights is the line of sight requirement. To be able to actually cover that kind of area, you really have to have a good sight line to the aircraft. And we found on a number of projects where even just having line of sight for some of the shorter flights with the LiDAR sensor has proved very difficult. There's also a lot of work that goes into booting up the system and getting a GPS lock. So it's not kind of the thing where you want to turn it off, move, and then turn it back on again if you can avoid it. So one of the challenges right now is just without the beyond line of sight, without the legal authority to operate beyond line of sight, we haven't found as much of a need for the fixed wing platforms as we would if we had that kind of capability. We have requests in to be able to do that, and the FAA regulations may change or may get a little more permissive around that over time. But for the short term, at least for most of the projects we've been working at in that, let's call it under 500 acre world, you know, we found pretty good ways to capture that with either multi-rotors or some of the smaller fixed wing photogrammetry platforms.
Okay.
Yeah, Leslie, I'll just add a couple of wind down things here. So I think my takeaways would be, you know, looking at the temporal advantages of UAS. As people know, you know, we can get out there for rapid response, and that includes LiDAR. So I think that's a plus of these small UAS LiDAR rigs that we're starting to see more of, and also the time between traditional public data access sets might be 2 or 3 years still. We're still filling in those gaps for customers with LiDAR, and I think that's where the LiDAR is achieving some of the best results. But the obviously cost is of importance, safety, and quality of the data as usual. And I can send to anybody if with contact information, a spec sheet on the LiDAR rig we have and the outputs we generate, as well as the FAQ we developed when we first put this together this summer, as well as our contact information. Yeah, and thank you, Leslie. Congratulations on your move to new pastures soon here as well. So thanks for hosting.
Thank you. Thank you both, Ian and John, and thanks for everybody who showed up and asked great questions. As I mentioned, this is being recorded, so the recorded webinar will get posted at VCGI's YouTube channel probably sometime this afternoon. So hope everybody has great holidays and a great day today. Thanks.